So hi, I'm Matt, and I'm going to talk a little bit how you could build a bank with Go, which apparently is a thing you can do. I didn't really think that would be the case 2 years ago, but yeah, it's a thing. So, little quick introduction. I'm Matt. You can find me on Twitter here. If you have any questions, give me a shout. I mainly work as a back-end engineer, do a lot of infrastructure and kind of back-end systems. And I've been doing that for a few years. And I've been working with Go for kind of 4.5 years, pretty much full-time for the last 4 years, which for me has been kind of amazing. I was a PHP engineer before. I say engineer very loosely there. No fault for PHP, but my ability at that point was terrible. And for me, Go has kind of changed the way I think quite a lot about programming, and it's kind of different kind of approach that it's given me. Has anyone heard about Monzo? Okay, so a few people. Cool. So I work at a company called Monzo. We make these kind of hot coral debit cards, currently prepaid, soon to be full debit cards when we release current accounts later this year. And we're a bank. So the main reason we kind of started this whole thing to like build a new kind of bank is mainly because this is how I see banks. And yeah, I mean, they look pretty fancy. And this for me is kind of as a guy with slightly crazy eyes. And for me, anytime I interact with my bank, this is kind of how it feels. Occasionally I have to go physically to a bank, which is quite annoying. And even if I don't, then I have to ring someone up, or my internet banking's not really that great. And ultimately, the kind of customer experience that I expect from banking in 2017 is not what banks deliver. In a world where like I can tap on my phone and a car arrives to pick me up, and while I'm in that car, I order some food on my phone and it arrives at my house by the time I get home. But like to even deal with my money, I have to physically walk somewhere. A bit lazy, but that kind of is a bit crazy for me. And there's lots and lots of reasons for that. Banking's an interesting business where kind of banks tend to consolidate quite heavily, which means you end up with lots and lots of different IT systems that have to be managed by kind of a whole team of different people. And at the core of that, we have like super awesome mainframes, which are really powerful and insanely expensive. But cool fact, if you wrote code that ran on this in like 1960, you can still buy a mainframe that will run your code, which is great if you don't really want to change things. But if you actually need to then interact with that code and kind of modify how your business works and kind of stay up to date, that is very difficult. And you end up in this kind of standard place where you've built up technical debt, and it's very, very difficult to kind of get out of that. So we started building Monzo about 2 years ago, which was back in February 2015. Getting a full banking license takes a little while. We kind of got our restricted banking license in August last year, and we're kind of working through with the regulators to get those last couple of restrictions lifted. And hopefully that will happen very soon. And then at that point, we are a fully regulated bank. We can issue current accounts to people, and you have all the kind of standard protections that any normal high street bank gives you. So what do we do that's different? So to start with, we give you an app, and everything you do with Monzo is through the card. Through the app on your phone. So this is one of my kind of fun features, favorite features. You can, if you have your card and if you lost it, you can freeze it, and then if you find it again, you can turn it back on, which is amazing. And kind of like it's just something that like obviously every bank in the world should provide and should have provided 10 years ago. Where I don't really need, if it sits down the back of my sofa, I shouldn't really have to wait for like 3 days for a replacement, or like 5 days probably, for a replacement to arrive. So lots of kind of little things like that are what we're trying to do to change the world of banking. So we have an app, we show you like where you actually bought things, so you understand where you've spent your money. We give you like kind of budgeting advice. You can send money through the app, in which case you get like James's face if you send James money. We have like fully built-in search. Again, this is like just kind of standard stuff that you have building anything that wasn't a bank, you would build into your app, including the ability to search with emoji. Oh yeah. And like when you've actually bought something, you can see like on a map where it was. So there's no more like confusion around like, what is this thing on my bank statement? You can also attach receipts. I attach photos of my brunch, which again is super useful. And yeah, as I mentioned before, you can like, if you lose your card, you can freeze it literally with one tap. And if you find it, you can one tap and it unfreezes. Or you can just order a replacement. You don't need to speak to anyone, just comes in the post like the next day usually. And that's kind of it. So all of these things seem like relatively straightforward. Like if you're building kind of any kind of internet-based app, like there's a huge range of different technologies you can use, and they're all like pretty standard. But like how do you start that if you're building a mobile app? So usually you'd have an application of some form, let's say Rails, whatever. And behind that, you're going to have some kind of database that's going to store your customers' data. And over time, that's going to get much larger. It's kind of the inevitability of like adding features and functionality to your application. And that's kind of going to increase in complexity. You might have multiple databases. You might need like kind of search things, caching, all sorts of other like really important features. And ultimately, you end up in this horrible world where you have this monolith, kind of this huge application. Now, that's not always a bad thing. Like, right at the beginning, if you're a startup, this is not your problem, right? Like, you don't have any customers, so like, building an application that people actually use, that's the most important part. But at some point further down the line, you end up with lots of complexity. And this is kind of a very, very common pattern. Loads of people here have talked about that in the last day or two. Loads of other companies have kind of talked about this situation where they have to like re-architect at some point in the future. And this is pretty much what happens. And this is my face. And ultimately, it's a really bad problem for developers because if you're a developer day to day, it's just so frustrating because you have to, like, you want to do like lots of kind of different things. You want to like add a really cool feature, and then you can't deploy it because like someone else is kind of dealing with something, and you have to like deal with one horrible release pipeline. So standard thing, we kind of break this up into lots of discrete services. I hate to say microservices, some size services. And these will be communicating in a variety of different ways, potentially, depending on how your application works. And this is basically how we started. So it's certainly not a perfect system if you start from day one building lots of small kind of web services that communicate to each other. You have a very big kind of amount of upfront work to do. And that amount of work is getting a lot smaller as tooling's kind of getting progressively better. But there's a lot of work to do if you want to like start off with a load of applications that communicate to each other. In our case, getting a banking license takes a really long time. So we had like slightly more time, which meant that we could kind of build a kind of platform which would allow us to then kind of scale this out without having to re-architect it at some point in the future. So while we were kind of going through this, we have a kind of few basic principles, single responsibility principle, so every one of our services does one job, does it well. Within those things, we are bounding the context of each application, so we're taking a discrete area of functionality in our app, building a service that supports that, or a number of services that are not kind of sharing functionality across boundaries there. And the cool part about that is we then get like really well-defined interfaces between our services, which also means if you're scaling out your development team, you have very well-defined interfaces and teams can do stuff without needing to like interact with each other. So how does that involve gophers? So if anyone hasn't seen the Go Gopher, this is the Go Gopher, the mascot of the Go programming language. And the real question is like, why would we use a relatively new language to build a bank which is like super risky? And actually, there's a number of reasons for that. We want something that is kind of memory managed. We want something that's statically typed, so we don't get like number conversions accidentally. That would be quite bad if you're a bank. We also are building a microservice architecture, or at least we're building a number of discrete systems which communicate over a network, which means we realistically need pretty good concurrency. And because we're building small services, we want them to be very, very lightweight. So obviously, memory management has been a really good thing, kind of demonstrated quite recently. We don't really want like buffer overflows because they're quite bad. And they've been in the news recently. I won't say why. But as far as like lightweight goes, we have a lot of different applications. And if we're using something like the JVM, then we're going to have every application is n 100 megabytes of memory, whereas Go services, you can use like 20 or 30 megabytes of memory, and that's the whole application running. They can also run like huge, huge numbers of requests and pretty much scale linearly with the number of cores. So some of the features that we're looking for in our language. As I mentioned, we're running network services. We're doing a lot of network communication. So we need these things to like, be pretty good at concurrency, especially in our like network services. So has anyone heard of Goroutines in the Go programming language? Okay, so quite a few people. Cool. So if you're doing concurrency, a standard concurrency model would be to use something like threads. Or if you're doing an extremely high throughput server, like in C, you might be using a small number of threads and like kind of polling with epoll or something to kind of minimize the number of OS threads that you're running on an operating system. And the reason for that is because threads are very resource intensive. And if you're scaling like your servers, that you're scaling out your number of requests with the number of threads, you're going to hit like the limitations of physical hardware relatively quickly. Lots of languages provide alternative ways to do that, and Go provides Goroutines. So Goroutines are essentially lightweight, concurrently running functions, essentially coroutines, which are then multiplexed across a number of threads by the Go runtime. And what that means is you don't really have to think about it. It's just kind of magic that magically happens. The runtime will take care of running a number of threads based on the number of cores that you've allocated to the program itself. If you're dealing with I/O over a network or reading from disk, again, the runtime will deal with threads for that part. But the actual functions that you're running, your business logic that is doing all of this, will be multiplexed over those threads without you having to deal with it. And it's extremely efficient. There's very, very low switching cost. And the Go scheduler is kind of quite optimistic on how it will move between executing Goroutines. So to demonstrate how easy that is, let's assume we have a function call in our code somewhere, and we would like this to run at the same time as the calling function. So we're going to put Go before it, and now it will run concurrently. Magic! And of course, now we just have, I mean, that's great, but now we've also got all sorts of problems of concurrently running programs. We have all sorts of like concurrent variable access and all of those kind of things which are kind of slightly harder problems. But the Go language makes it extremely simple to do this, and you can run like hundreds of thousands of Goroutines concurrently on a reasonable amount of hardware. That's a perfectly realistic amount to run. So as an example, the HTTP server will be running a new Goroutine for every single request that comes in into a HTTP server. They're extremely lightweight, so when you create a new Goroutine, it's going to allocate a very small amount of stack memory. That's going to grow dynamically and contract dynamically, and it's usually kind of like 8K or something like that, compared to like a megabyte or like half a megabyte, which is allocated when you create a new thread. So in our, say we have a main function in our main package. This is kind of what Go programs are like. And we want to run this handle request method. I'm going to run that concurrently. Essentially, our flow will be our main outer function will run, and then this will run at some point concurrently, probably on another core, and then it will exit, and the main program has carried on running during that time. So as I mentioned, when you're then using shared values, you potentially have a problem. You need to kind of coordinate access between potentially hundreds of thousands of different like coroutines. So the kind of mantra in Go is to not communicate by sharing memory, but share memory by communicating. And what this means is, instead of like having a global variable that is protected by mutexes or kind of some other kind of locking mechanism, we should pass values between our executing Go routines. And Go will take care of the kind of access to those variables in that case, so that only one Go routine will have access to the variable at that time. And Go provides a really nice way of doing that, which are channels. So channels are essentially a pipeline that you can put something into and it will come out the other end. And usually you'll have one Go routine which is doing lots of stuff, and it will stick something in and it will come out in a different Go routine which can then work on that value, and then it may go somewhere else. And they're extremely simple, but they allow us to do like a huge range of different kind of design patterns in our application. So in this case, I have two gophers who are shouting at each other, and we're going to pass something from one to the other. If we had a pipeline of different kind of functionality, we could have one Go routine that's doing lots of things. It has the kind of results of that, that kind of functionality. It's going to pass it down a channel to another Go routine, which will then do some more functionality, and then those results can be passed down again to another one. And they can be either, in this case, synchronous, or you can actually allow your channels to be buffered, in which case you can size the amount of messages that can be fitted in the channel. And as long as there's space in the channel, then your kind of Go routine that's putting stuff in will just put it in, it's non-blocking, and it will carry on working. And as soon as it does fill up, by default it'll block until there's space in the channel. Or there are kind of other mechanisms that allow you to kind of have a different case if the channel's full. And that's quite cool, because it means like, actually, if, so I don't know if anyone's used the queuing technology called NSQ. No, okay. So NSQ is like a quite high throughput messaging system. By default, on a topic, it has 10,000 messages in memory. And then once that's exceeded, it puts the rest on disk. And that's actually using a channel. So it has a buffered channel with 10,000 slots. And as soon as that's full, it starts writing the messages to disk instead. And that's quite cool, because that's like about this much code. It's like literally 3 or 4 lines. And that functionality is just kind of super simple to write. So the other thing channels allow us to do are kind of different patterns. So this would be like a fanning in pattern, where you might have lots of different workers that are generating things that then a single worker that perhaps has coordination can then use the results of that. Or equally, if you have something that's generating loads of work, you can have multiple workers which again are pulling messages off this channel. And you can then scale these things independently within the process of your service. So the other cool thing for us for Go is that the language itself is extremely simple. So if anyone has started using it, you can go on the Golang website. There's like a 70-step kind of tutorial that's in the browser. That starts off like really, really simple, and then it will take you through like kind of concurrency patterns, some pretty cool like maths puzzles, and the language itself is like really, really small. And the thing I like about that is, in the case of like most of the programming languages I've worked in, there's like a million different ways you can solve a problem. And I kind of, this is probably entirely my fault, but I find I spend like some amount of time working on the actual problem, and then the other rest of the time trying to make the code more idiomatic, because I think that's what it should be like. And in Go, I just don't really have that choice. Like, there's kind of, the language itself is extremely small, the syntax is very, very simple, so there's kind of almost a natural way to solve a lot of problems. On top of that, when you build a Go programming, you get a single executable binary. So if you are shipping a huge number of different applications, you don't have to ship around like an entire source tree and a runtime and make sure the runtime's installed on the servers and all of that kind of stuff. You get a single binary which you can just run. Now, a lot of those problems are kind of taken care of by running all your applications in Docker containers, which hopefully everyone is. But in the case of Go programs, you actually don't really need to do that, because you don't need a runtime. The runtime is built into the binary. As long as you compiled it for the right architecture, you're kind of problem solved. And that means like, if you did write your, like compile your program, your deployment is pretty much compile, put in S3, hope S3 is working this week, and then put your binary on your server and run it. And that's literally it. On top of that, the standard library has huge amounts of functionality. So although the language itself is really small, the standard library provides everything. You can spin up a HTTP server in like 3 lines of code. That will automatically upgrade clients to HTTP 2 since Go 1.7. Magic. It's kind of just done. And all of those things kind of have extremely sensible defaults that you don't really need to fiddle with. But if you want to kind of customize the dial timeouts on your HTTP clients, you can do all of that yourself manually. So for us, like, having that simplicity is really important because as we've been building our services and our infrastructure over the last 2 years, things have got progressively more complicated, which obviously is kind of the inevitability of building a large application. So I mentioned before we have a microservice architecture. In February, we had no services, obviously. And then progressively over time, we're up to like 190 something now. And each of these is a discrete Go binary, single process that can communicate over HTTP to any of the other services. So if you're kind of starting with this, there is actually a few kind of tools you can use. There's GoKit, which I don't know if anyone's heard of, which provides you a kind of toolkit, pretty much like a framework that allows you to build simple services, but then plug in the more complicated things you need for kind of distributed systems, things like tracing, logging, like all of those things to kind of instrument how your code is working. There's also Micro, which is, again, a microservice toolkit. This one comes like more fully featured by default, and then you can switch things out if you don't really like the way that they work. In our case, these unfortunately didn't exist when we started building our infrastructure. So we have a really simple kind of library called Typhon. That's on GitHub. And all that is it allows us to build really simple HTTP servers and clients that are kind of pre-configured in the kind of way that we use them. So if we have a kind of service talking to another service, a lot of this happens in our infrastructure. These are communicating over some form of transport. Now, in some cases, that might be a message bus. You might be using something like RabbitMQ, ZeroMQ, something like that. However that works, you're going to realistically be communicating to more than one copy of every service. And hopefully you're doing that because any one of these could fail at any point, especially if you're running on kind of cloud infrastructure. That's kind of a good thing, that it fails, networks are unreliable, and basically by kind of knowing that and building that into your application, you can make your applications much stronger as a result. So in our case, we have a client and server library. This is that Typhon package that we use. And we're actually communicating literally just with HTTP. But the problem you have is, like, when you're building a microservice architecture, you need to build a huge number of things into these clients and servers to make things reliable. Stuff like service discovery, load balancing, timeouts, rate limiting, circuit breaking, failure detection. Like, things are extremely unreliable and things break all the time. And if you're building a bank, unfortunately, that's not really an option. Like, your applications have to be very, very resilient. Ideally, they would be quite quick, but even more ideally, requests will succeed within a kind of bounded amount of time. So in our infrastructure, we kind of, a big question mark here, we can either build all of these things ourselves automatically, like into our actual services, or there are a number of tools that you can use in between these which kind of take away a lot of that complexity. And that's actually what we want. We want to make our services as small as possible, which means we can just write small HTTP servers that live here, and our application development is then super fast and super quick. So in our case, we use Linkerd. Don't know if anyone's heard of that. So it's basically, if anyone's used Finagle, which is a Scala kind of library that came out of Twitter, that provides their like RPC between processes. Linkerd wraps that up in like a sidecar process you can run on a host and allows you to kind of does all of that stuff without you really dealing with it. And it's very configurable, and in our case we use Kubernetes, so this is plugged into Kubernetes as well, so it knows where all of our services are, and I'll come on to that in a little bit. In our infrastructure we have a load balancer at the top. We run on Amazon, so just in the LB, and behind that we have a kind of Go-based HTTP layer, which is going to take in HTTP requests and decide where they're going to go and route them within our infrastructure. We then route that off to what we call an API service. So this is, again, just a small Go server, which is listening on a port in a container in Kubernetes, and it takes in requests and then probably un-JSON marshals them, does some stuff, returns some kind of response. Yeah, kind of like, I think 90% of what we do, and probably what everybody does, is basically marshal JSON into a database and then back out of a database. And that's kind of what happens here. So JSON. And then in our case, what we don't want to do is change this routing layer right at the top every time we add functionality to our application. We want this to be the most stable possible thing that can deal with potential failure further down our infrastructure. So instead, we deploy individual API services and we route them based on name. So in our case, we have an API. If you've signed up for a Monzo card and have an account, you can literally go to the kind of API docs. There's a developer portal. I've got the wrong URL there. But you can go to this. You can get full access to your data as you spend it, as you use your card all around the world. And in this case, I'm using a webhook. So I can register a new webhook, which will then make real-time callbacks to an app that I've built as a third-party app. So while I use my card in a till or in a shop somewhere, I'll actually receive a HTTP call realistically before the receipt has printed out of the machine. So this is literally /webhooks on our API. Now, if we want to add lots of extra stuff to our API, we don't want to change our routing layer. So what we can do is we route this webhooks thing to a service, which is just a Go binary, and that will deal with webhooks for us. And if we want to add a new thing, which is like, I don't know, /ponies, and we have like a highly available pony-based API, we just deploy a new service. And our API will see it's there using service discovery, and then it will stop 404ing those requests. It will route them through to the correct application. So in our case, this is the webhook API. And then behind that, this will do some kind of business logic. Realistically, it's going to like check that you're actually a valid user, and then register or deregister a webhook for you, and do all the validation there. And these services can do anything they want. Again, they're just standard Go HTTP servers. And behind this, they're then using either a database or some kind of external provider or anything like that. So in our case, one of the kind of really cool functionality in Go is you can just define really, really basic interfaces for kind of any data type, really. So in our case, we define any of these functions, like essentially HTTP handlers, to literally just be a type of service, which is a function that takes a request and returns a response. And that's all it does. So I can do anything I want as an application developer. I don't need to like kind of think of like do anything really complicated. I literally just register a thing that takes a standardized request type, does anything, and then returns a response type. And then when we're doing kind of registering these in our Go service, we can just register like get / would be to list them, post would be register a new one, delete with an ID would deregister one. And this is just using, there's quite a few different like routing libraries for Go. You can use like either Gorilla or like Gorilla Mux. There's a couple of different ones. But as an application developer, I can create a new service like with a single command. I can then write a couple of handlers, which are just simple functions. I can compile it, push it through CI, and deploy it realistically within, like, well, if it was super critical, maybe half an hour, probably less. And that's incredibly liberating if you're an application developer. If you don't have to, you've gone through like all the kind of the checks and balances. We obviously have code review, and we're asserting everything in our normal infrastructure works, even after the addition of my new code. But being able to do that extremely quickly is like that's kind of our advantage. Like our competition is huge Leviathan banks that spend billions of pounds on IT every year. And the only real thing that we have going for us is like speed. Like we can execute really quickly. And that's what we need to be able to do in order to kind of stay ahead and provide a really good experience for customers. So being able to do stuff really quickly is super important. The other point is making our system really reliable. And if anyone has built microservice architectures and sent lots and lots of calls over the network, that's generally not very reliable. So we have a bit of kind of a trade-off here. Now, in our case, I mentioned earlier, we use Docker and Kubernetes. So we build all of our individual services into a Docker container. Cool thing with Go binaries is because you don't have to have a runtime, your containers are literally the size of the binary. You can use a scratch container. That also means you don't even have a shell in your container. So if, hopefully this never happens, but if there is some kind of like breakout or escape vulnerability, you kind of break out into a container that doesn't have a shell, which is largely infuriating. And the other thing is then they're really tiny. So we can ship these around in Kubernetes. You run them in pods. You can still do like all the kind of, if you need to like, I don't know, TCP dump a HTTP server, but you don't have a shell in the container, then that's fine, because in Kubernetes you have a shared network namespace within pods. So you can run like a special TCP dump container in the pod, and you can like TCP dump the interface that your actual service is using, which is quite cool. And in our case, we switched to Kubernetes actually from Monzo a little while back in August last year. And this is kind of our previous infrastructure, which was starting to get quite expensive. And we switched over to Kubernetes, and that's worked out about a third of the cost of our previous infrastructure. And that's mainly because we can condense things a lot more densely, but we still have things like pod auto-scaling, so our individual services can scale within the constraints of our main infrastructure. So to go back to my previous example, if I'm registering webhooks and I want really reliable webhooks, then we're going to run a number of copies of these services. So this is just, again, a pod in Kubernetes. We're running many copies of that. And let's say that this one fails, and then all requests going to this are failing. If it actually vanishes, or like the host machine vanishes, then Kubernetes will deal with that, and it will spin up a new pod for us. And then that'll kind of propagate through service discovery. Our services will find out where it is, and requests will go through to that. The other case is we might have, that one's dead, we've got a new one. This one is particularly slow, in which case the other thing we need to make our system more reliable is going to be some kind of either circuit breaking, or ideally kind of a load balancing on the client to decide which instances are best suited to serving our individual requests. In our case, Linkerd does that. It has a power of two choices exponentially weighted moving average load balancer, which who knows what that does, but it's like super great. And the main thing it's doing is checking that like these two are faster, that one's slower, so send requests here. In some cases, that might be routing a request on a single host, and there might be a copy of the kind of receiving service on the same host, and that might not be the fastest one. So it will send it across the network to a different machine, and that will just happen automatically. So if you're building, again, like distributed infrastructure, like distributed architectures, you have to be aware of these problems, and you need to be able to either have things that will retry if they're idempotent, or like deal with the fact that some services are going to be slower than others, especially if you're kind of running in cloud infrastructure where you might have one host that is officially the same but much, much slower because it's more heavily loaded. The other thing we do is we try and push as much stuff kind of to be as decoupled as possible by moving it to being a kind of event-based, event-driven architecture. And this means we can do things like, if something is down, if a system is down and it's not of critical importance, we can buffer messages and deal with them later. We can process things asynchronously that don't need immediate responses. And all of these things mean that we can still do them within a reasonable amount of time, but that we can provide a better, more reliable experience to customers. So actually in the case of, so similar kind of thing, we'll have some synchronous call that comes through our API to, again, just another Go service. We're going to route that through, maybe it does calls to these two services. And as a result of some kind of action in our infrastructure, we'll generate an event that this has happened and publish that onto a message bus. So let's say this was creating a transaction. That's obviously going to go into someone's like app on their like bank statement, pretty much. So we can publish that this transaction has been created, and then any number of things downstream of that can consume that. And this is completely decoupled from the consumers. So we can build any new functionality and deploy that, again, entirely separate of our core transaction flow, which obviously needs to be super reliable. However, the problem we have here is any number of things could be happening here. And if you have a system that has hundreds of microservices and you've decoupled with consumers and producers, you probably have no idea what's going on. Like, I have no idea how our infrastructure works. I know how some sections of it work, but we have lots and lots of developers, and that will grow infinitely more complicated over time. And we need to be able to test that, and we make sure that our synchronous and kind of core transaction flow is extremely reliable. But fundamentally, the flip side is we need to be able to empower developers to build stuff really, really quickly. And decoupling this kind of makes that much easier. So in order to understand how our infrastructure works, we need to kind of trace things through that. Now, Go provides kind of a way of doing this with contexts. So Go 1.7 actually pulled this into the main standard library. For a given kind of request path, we need to understand how this is flowing through our infrastructure. And in the case of something coming into our API, going to one of our API services, doing some JSON stuff, and then hitting something that actually does real work, at the top of our API, we can tag something with a unique reference, kind of a request ID. If anyone's used kind of tracing systems like Zipkin, basically something like that, we pass that then down our request tree. So we'll, at this point, generate the ID, marshal it into the headers, send it over the wire, unmarshal it, pass it through every function call in this context object. When it comes over to this point, marshal it back onto the wire, send it down. And that means even though these have been running on different machines, we can still tie together different requests across different services. So in Go, you can use this context. There's a kind of context interface, so you can actually build this into any of your own custom types. So our request type implements the context interface, which does lots of stuff, which we don't really care about. But the cool part is this. So you can stick any key value into this object. It's immutable. So every time you modify it, it actually copies itself internally, which means it's thread safe. And you don't have to worry about that as you pass it around. So a kind of a common pattern that you see in Go is for a lot of functions to have the first function argument as a context. You pass in this context object, and that means that then any further callers have access to potentially any keys and values. So you kind of define like request ID or something like a well-known key, and then you can try and pull that out. And if it's there, you could log that, and if it's not, hey-ho. So obviously the reason you need this is because Go doesn't have thread local variables, so pros and cons. But that's because we're running in coroutines rather than threads. So assuming that we have our request ID available all the way down, we can then, at each one of these points, kind of instrument various kind of pieces of information, like the time that we received the request, sent it on, received a response, sent it back. Obviously, we can only correlate times on individual nodes because of clock skew. But we can then tie those together because we know that that send happened before this receive, so our system can kind of correlate them. And in our case, we aggregate all of this together. So you could use something like Zipkin for this. And you get a huge block of data that's completely unintelligible. And obviously, humans are not meant to read stuff like this. But given that you've done that, you can then kind of reconstruct that into some kind of call graph. And this is calling across lots of different services. So each one of these is, again, a different Go binary. We've got HTTP server, HTTP clients, all the way down. Again, really straightforward, kind of simple standard library stuff. And what we're actually modeling here is this first section is a synchronous call for using a card. So if you have a card, which, oh, maybe I do, maybe I don't. I don't, okay. If you've got your debit card and then you stick it in a machine or use contactless, at some point, we're going to receive some form of HTTP call from that. At the moment, we receive them over HTTP as SOAP, and we pretend to be a SOAP server. And unfortunately, that's the way that the banking world works. If you connect directly to payment schemes, realistically, you'll be doing like really low-level socket stuff. Quite often, you have to use like EBCDIC encoding because ASCII is like way too modern. And the result of that is some kind of payment instruction from a card machine. We then have to do a few things. So we need to look at the card. We need to make sure it's not like blocked completely. We need to make sure you've not frozen it. We then obviously need to create transactions, update your balance, do all those kind of things. But then there's a lot of other things we do in the app which we don't need to do right at that point. So in the Monzo app, when you use your card, we display like the merchant logo. We display like a really nice name. We kind of show you on a map where the merchant was. We don't need to do any of that right now because that's kind of irrelevant for your card working in the shop. And I'd prefer my card to work in the shop than get a pretty map. So at this point, we can respond back to our payment provider. And we can do all of that synchronously. But during that, we'll publish a message that says this transaction was created with some kind of basic amount of information. Then further down from that, we do this like transaction enrichment step where we'll kind of correlate it to a merchant. We'll like look up the merchant details, try and kind of work out where that is, do all that kind of stuff. And then at that point, we'll insert it. We'll actually kind of fire another event. And then at that point, we'll insert it into the feed in the app. So the interesting part is actually, if all of this was broken, your card would work, but it wouldn't appear in your app. But that's kind of okay because your card worked, and at some point in the next like couple of seconds, hopefully, it'll appear in your app, or your app will be out of date for a little while. But in the real world, like, it's going to be a short period of time. Worst case scenario, we're down for hours, but your card still works, and we still have the right balance, but just your app's kind of a bit out of date, which like realistically is like a good way of making our systems a lot more reliable. And then after this, we send you a push notification. And the cool thing is, although this looks really complicated, you get a push notification. This appears in your app usually before the receipt has printed out on the machine because computers are really fast and like banking networks are really slow. And here we have a coffee cup emoji because it's at Starbucks. So we know it's a coffee, so we gave you a coffee cup emoji. And people love this. Like, this is like our best feature. If you buy stuff at Etsy, you get a sushi emoji. Like, true story. And we do all of this like before the receipt comes out of the machine, because again, like, computers are quite fast. You can do stuff like this really quickly. It takes like 200 milliseconds. And yeah, that's pretty straightforward. So this is, of course, like a massive lie. This is actually what happens. And actually, that was a couple of months ago. I have no idea what some of this stuff is. But things like if you have budgeting enabled, we'll check your budgets. We'll like see if you're above or below target. We'll send you like kind of praise if you are, something like that. We'll look up new merchants. We like get all of that information. And all of that stuff happens before you get a push notification, because like if you're doing spending analysis, like the push notification contains that information, so we have to do it before. But even if all that's broken, your card still works in the shop. So it's all good. So in our case, we've kind of started using Go. 99% of our services are in Go. We've got one or two that aren't. Because we run everything as really basic HTTP servers in Kubernetes, and we have like our service discovery is separate from our actual business logic, we can write stuff in like Python if there's like kind of machine learning, data analysis, that kind of stuff. That's way more suited to that. If we're dealing with IBM MQ, then don't use the Go library for that. There's like really good Java libraries. So like use Scala or Java for that particular thing. But in our case, like Go has been kind of perfect for like that kind of microservice architecture. It's allowed us to build stuff really, really quickly. The kind of concurrency and the like kind of features it provides as a language really like built into the language. Let us build highly performant, very scalable, very lightweight services, and build them really, really quickly. And the language itself is like really small and simple and easy. And that's meant if we're onboarding engineers, like even if you've used the language before, when you start another company, like inevitably there is like some wonderful homegrown framework that you have to learn. And it's kind of like inevitable. And in our case, like, sure, there is some of that, but it's so simple that like, even though you're learning a new language potentially, and you're learning potentially new framework, like people are productive within like a couple of days and are deploying to production within a few days, or usually a day or so. Yeah, and so that's about it. Thank you very much, everyone. Yeah, so if anyone's got questions, if the question is, do you have Monzo cards? The answer is yes. Cool.
Once you've got your banking license, you have sort of immediate plans to offer credit facilities?
So the question is, once we have the banking license, will we do credit facilities? Yeah. So we are planning to offer overdrafts, but we won't initially be doing like things like loans or credit cards. Like our aim is to like build the best possible current account and like really like nail that. But yeah, overdrafts is a part of that.
Hello, I'll start again. So you talked a lot about using RPC over the network and using Linkerd and stuff like that, and getting stuff out quickly to prod from development. But there's kind of been less talk about doing this while ensuring that the security in between, like doing client authentication or protecting against lateral movement. I'm curious how you're maintaining like this velocity while also protecting like the security of your users.
Yes. So I guess there's a lot of different areas of that. Like security is a pretty wide topic, and we have a security team that kind of works full time on that. So both in the client itself, obviously clients are untrusted. Like we can't trust anything that our clients send us. However, we can build in lots of functionality into that, things like Touch ID and that kind of stuff. Actually, in our infrastructure, I think one of my colleagues, Simon's, done a couple of talks about how we segregate Amazon access. So you can separate people who can manage users versus people who can provision users and give them roles. You can do those in separate Amazon accounts, so you can separate that kind of thing. Within there, you then have all sorts of network policies. In Kubernetes, you can use Calico to do network policies between services. Even below that, you then have to like kind of prove who you are within an infrastructure that's essentially a big soup of stuff that can communicate. And Kubernetes provides a little way of doing that, but it's not really kind of established enough. I don't know how far we've got with it yet, but we do like client authentication with certificates that rotated between services, which means we do like a lot of kind of CA stuff internally. And you can keep parts of that offline, like root keys and things. Yeah. I don't know if that's really answered your question. Like, essentially, there's a lot of stuff you have to do. And ultimately, if you have like 200 services, each of which you're running between 3 and n copies of, you're realistically running like a couple of thousand binaries across a number of machines that can all make HTTP calls to each other. So yeah, they have to have relatively strong authentication, and you have to know something is who it says it is within the infrastructure to guarantee that.
What countries do you operate in?
So at the moment, just the UK, I'm afraid.
All right.
But the cards work globally. So I'd say that's one advantage of like, our cards are all MasterCards, which means they work in every machine in the world pretty much, versus like building your own point of sale devices. We can't give you a card if you live in another country yet, although hopefully soon. But the cards will work anywhere in the world, and like you can't get a better exchange rate, as far as I'm aware.
Hello. You mentioned that you are using Linkerd with Kubernetes. Can you elaborate a little bit? How do you deploy Linkerd in a Kubernetes environment?
Yep. Yeah, so we run Linkerd locally on every machine, which means you run it as a daemon set in Kubernetes. So that means like as soon as you bring up a new node, Linkerd pod launches on that, runs there. Obviously, you can't communicate to localhost because that's not a thing in Kubernetes. Like every pod has its own IP. So the pod manifest for the daemon set like works out what the local linkerd is given the subnet and provides that as a proxy address to all of the pods that run on that machine. So that means all of the things know where the local linkerd is, they communicate to that, and then that uses the Kubernetes namer, which linkerd provides, which hits the Kubernetes API, which gives you service discovery. So it then knows where all the other pods are. And if it's communicating from this service to that service, it'll go to the local linkerd, go over an established TCP connection to that local linkerd, and then to that one. So the whole point is like to stop opening socket connections with your infrastructure, which is like relatively slow.
With that many services, how do you handle automated integration testing end-to-end? Automated integration testing. So say, do you test the entire flow with that many services?
So we have lots of different flows. And yeah, you basically have to write something that can run your automated test suite like against your production infrastructure. I think actually Greg talked a little bit about that in the failure track yesterday. Yes, we have a test suite that does both individual unit testing, but also acceptance tests. That's the word I'm failing to remember. In a microservice architecture, like unit tests are great, but like they essentially prove that like, the really tiny amount of functionality works, which is ultimately useless because the bugs that you have are like between the interfaces. Like you've changed something, it provides a parameter, this isn't expecting it, it explodes. So yes, you have to have full acceptance tests. We have those. We run those on CI as well, on every single kind of commit, which is time consuming, or at least not if you provide enough power, so I guess expensive. But that means that we have flows that test everything the app does, everything the core, like card flow, all of those kind of things, all the admin stuff. And those are run against a set of, we run every single service against a set of Docker containers which run all of our shared infrastructure. That's spun up on CI every single time. That tests that you, in theory, have a working set at that precise commit, but it doesn't assert that if you deploy that commit and that commit in production, then makes that it would work. So then, yes, realistically, you have to then build a system which can take those acceptance tests and run those as kind of tasks against production. We do some of that in production at the moment. So we'll do like, we simulate customer behavior. And once we have our actual card processor, because we're in the process of directly connecting to MasterCard, we can then simulate full card flows without going through separate infrastructure. So we'll do both like, hey, here's an actual card terminal. You probably see loads of videos online of like train track, which drives like a card around, goes past a card terminal, and that's hooked up to a monitoring system. We'll do stuff like that. But we can test also at the actual MasterCard point at that point as well, which would be kind of cool. Anyone else? Cool. Well, thank you very much. If you've got any questions, come and give me a shout.